This video deals with Newton's law of universal gravitation. Newton's theory was that the force of gravity, Fg, is equal to four terms. We have the universal gravitational constant, the mass of the two objects being attracted to each other, and r is the radius, or the distance from center to center between them. The reason why it's r instead of d is because oftentimes they're talking about planetary orbits. So some interesting things about this formula. First off, g is the universal gravitational constant. Big G is much different from the little g we've been using, the negative 9.8. So big G is 6.67 times 10 to the negative 11th newtons times meter squared over kilogram squared. That weird unit, you don't really have to worry about. It's just there so that when we multiply all this stuff together, do the division, we end up with newtons at the end of the day. The next thing is, since masses, universal gravitation constant, and r are always positive, the force of gravity is always negative. So it's always an attractive force. It's always reducing the distance between the two objects. It can never repel something, push something away. The third thing is there's no upper or lower limits to m1, m2, and r. Every object with mass attracts every other object with mass. You in the chair you're sitting in right now are gravitationally attracted. Lucky for you, g, the 6.67 times 10 to the negative 11th, is very, very small, or else there'd be a non-negligible force between you and your chair, making laziness more socially acceptable. So let's say we had two masses, spherical masses, and we know the distance between them. It just so happens that the masses and the distance, force equals 1. If we were to switch out one of the masses, make it twice as much, well, that's going to affect the force, and it's going to be twice as much. So if we increase the masses, we increase the gravity. If we double the other mass, then the force of gravity would be 4 newtons instead of 2, because every time we double, it's going to be the product. With radius, it's a little bit more tricky. So to find the radius, let's say we take the radius, reduce it by half, we'd expect that the force is going to become greater, because when we reduce the distance between two objects, gravity should be stronger. And that is what happens. But if we have it, it's not twice as strong, it's 4 times as strong. The reason for this is because the formula says force of gravity is proportional, that's what the little alpha is, to 1 over 1/2 r squared. When we square the 1/2, we get 1/4 r squared. When we divide by a fourth rather, we end up with 4 on top, so it's 4 times as strong. On the other hand, if we get further away, we should expect that the force of gravity will get weaker. And that's exactly what happens. But once again, it's not linear. It doesn't just go, oh, we doubled the distance, it's half as weak. Instead, when we double the distance, we end up with 1 over 1/4, and it's 1/4 as strong as before. So, using the formula, let's try a problem. We have Phobos. Phobos is a moon orbiting Mars. So we have the mass of both and the distance between them. If we wanted to find the force of gravity, well, the first thing to do is write down everything we know from the problem. Secondly, we know we're looking for Fg. It just so happens that we know a formula where we use all these things and Fg. It looks a little something like this. When we plug everything in, it's going to look like that. So it'll be 6.67 times 10 to the negative 11th times 1.072 times 10 to the 16th times 6.419 times 10 to the 23rd, all over 9,377,200 squared. What we're going to end up with is negative 45.90 times 10 to the 28th divided by 8.793 times 10 to the 13th. Doing the division, we get 5.220 times 10 to the 15th. And that should be a negative there. So, if we go on, I'd like to extend to you this problem. Instead of finding the force of gravity for Phobos, I want you to find the force of gravity for Deimos, the other moon orbiting around Mars. So you're given the mass of Deimos, the mass of Mars, and the distance between them. Now, I'm willing to bribe you with a piece of candy for doing this. It only lasts until the end of this unit. One per pupil, so I'm not going to give you a whole handful. And since I'm not giving you a whole handful, supplies are limited, so please act now. Thank you.